What does it take to see the universe's deepest secret? What happens when your quest for knowledge requires an energy so monstrous that it literally bends the fabric of reality against you? To see a tennis ball in the palm of your hand, the cost is negligible. A few photons of visible light, each carrying a tiny whisper of energy. About 2 electron volts to see this about 3 inches tennis ball. It's the energy a single electron gets from a standard battery, a trivial fee paid to the cosmos. But the universe operates on a brutal sliding scale. The smaller you want to see, the higher the price. And the price isn't measured in dollars, but in pure, violent energy. This is governed by a fundamental rule from quantum mechanics. The energy E of a photon is given by E equals hc over lambda. The h is Planck's constant, c is the speed of light, and lambda is the wavelength. The Planck length is a fundamental unit of length, approximately 1.616 times 10 to the negative 35 meters. The equation is simple, but its implications are staggering. To see the tiniest wavelength of an object, you must inject exponentially more energy. Let's take the descent. A grain of sand, 0.08 inches. Still cheap. Visible light still works. A bacteria? We're pushing into ultraviolet, maybe 10 electron volts to see these 10 micrometers bacteria. We're still in the realm of the ordinary, but now we cross into the quantum frontier. To resolve a single DNA strand, we need wavelengths smaller than a virus, about 260 nanometers. Let's jump to electron microscopes, dealing in thousands of electron volts, or keV. To peer at the nucleus of an atom wavelength, 10 to the negative 10 meters, we need X-rays and gamma rays, with energies in the millions of electron volts, or MeV. And now, we hit a wall. To see an electron, or the quarks inside a proton, you can't just look anymore. You have to smash. You have to take particles like protons and accelerate them to near light speed and collide them head-on. It's the ultimate act of scientific violence, shattering 2 exquisite watches together to divine the nature of their gears. This is the realm of the Large Hadron Collider, the most powerful microscope ever built by humanity. It smashes protons together with a combined collision energy of 13 tera electron volts, that is, 13 followed by 12 zeros, an immensely big number. And with this godlike machine, what is the smallest distance we can probe? About 10 to the power of negative 19 meters, a staggering achievement. But we are not even close to the bottom. Lurking far, far beneath this is the final boss of physics, the Planck length. 1.616 times 10 to the negative 35 meters. This isn't just another small number. This is the scale where the universe's very operating system crashes, where gravity and quantum mechanics meet and combust. So, let's ask the dangerous question. Let's use our trusty equation, E equals hc over lambda, and plug in the Planck length as our wavelength. What energy would a photon need to resolve this ultimate pixel of reality? The calculation gives us the Planck energy, and the result is a number that defies comprehension. Approximately 1.22 times 10 to the 19th giga-electron volts. Let's get a sense of scale. The LHC operates at 13 TeV. To probe the Planck length, you would need an accelerator 1 quintillion times more powerful. To probe the Planck length directly, a particle accelerator would need to be approximately 15 orders of magnitude, 10,000 trillion times more powerful than the Large Hadron Collider, or 4,000 light-years long. You would need to concentrate over 2 billion joules of energy into a single particle. That's the energy of a 500-kilogram TNT explosion, focused into a point smaller than anything we can conceive. That is so big, so powerful, a godlike structure, impossible to comprehend by any human mind. And this is where Einstein enters the chat with his famous equation, E equals mc squared, where E equals energy, m equals mass, and the c equals speed of light. As you increase the energy, the mass will be increased as well. Energy and mass are two sides of the same coin. You put immense Planck energy, and the mass started to grow. Instead of looking for the Planck length, you are creating gigantic, devouring mass. When you concentrate this much energy, this much effective mass, into a volume as small as the Planck length, you cross a point of no return. You cross the Schwarzschild radius. The Schwarzschild radius tells us the size at which an object's own gravity causes it to collapse into a black hole. The formula is R sub s equals 2gm over c squared. If you take the mass m, equivalent to our Planck energy, derived from E equals mc squared, and plug it into this equation, the Schwarzschild radius you get is exactly the Planck length. Your active observation, your ultimate microscope, would instantly and catastrophically collapse into a black hole. It would swallow your experiment, your laboratory, and any data you hope to collect. And here is the most beautiful and frustrating part of this cosmic censorship. If you try to cheat, if you say, "I'll use even more energy to get a sharper image," you only make the problem worse. More energy means more mass, which means a larger Schwarzschild radius. You just create a bigger black hole. The universe has built a perfect, inescapable trap for the curious. The Planck length is the final frontier, not because it is small, but because the very act of observing it triggers a law of physics that destroys the observer. It is the universe's ultimate keep out sign, written not in words, but in the fundamental constants of reality itself. It tells us that some doors may be forever locked, not by our ignorance, but by the very nature of the cosmos we seek to understand. What do you guys think? Let me know in the comments. And as always, don't forget to like and subscribe to Brainwave. Until the next time, take care.